In this lecture, we are going to look at the code to implement an autoregressive linear model for time series prediction. Since you already know how to write linear regression using PyTorch, that's not going to be much of a challenge in this lecture. The challenge in this lecture mostly has to do with processing the data correctly and making forecasts. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So let's get started. The new thing here is after the imports. We're going to start by creating a synthetic dataset. Remember how earlier I explained why synthetic datasets are important? They allow us to carefully study the behavior of our model under different controlled circumstances. So in this lecture, we're going to start with a very basic time series, a sine wave. To start, we're going to create a sine wave with no noise, just a pure sine wave with 1000 points. We also plot the series so you know what it looks like. Alright, so there's the sine wave. Next, we build our dataset. In this example, we're going to set t equal to 10, which means that we're going to use 10 previous time steps to predict the next time step. We'll start by populating x and y as lists, and then cast them into arrays once we are done. You could alternatively pre-allocate these as fixed-size NumPy arrays, but I've decided to take a more lazy approach. So in this loop, we go from 0 up to the length of the series, minus big T. Now of course, you want to double check that this is correct, so that we don't have an off by 1 error. The reasoning is this. We know that our input x will go from little t up to little t plus big T. So for example, 0 up to 10. In terms of actual indices, that will be 0, 1, 2, and so on up to 9 inclusive. So when we say 0 up to 10, it doesn't actually include the index 10. Instead, the target will be at the index 10. We know that the final index of the original series will be the final target. That's the index len series minus 1. Thus, in order for the final target to be the length of the series minus 1, that means little t must go up to the length of the series minus big T. If we plug in the final value of little t, we get len series minus t minus 1 plus t, which is equal to len series minus 1. So inside the loop, we assign little x to be the series from little t up to little t plus big T. Then we append this to big X. Next, we assign little y, which is the target, to be the series at time little t plus big T. Then we append this to big Y. When we're done, we cast x and y to NumPy arrays and print out the shape. So as expected, x is of shape n by 10, whereas y is n by 1. Next, we build our autoregressive linear model. As you know, it's just nn.linear. As expected, the next step is to create our loss and optimizer. Since this is regression, we'll be using the mean squared error. Next, we split the data into train and test sets. Here's another important point about training time series models. You don't want to split up your data randomly, say using the scikit-learn function at train test split. This wouldn't make sense because a real forecasting model has to predict the future. It can't train on points within that future. Thus, our model trains only on the first half of the dataset and validates on the second half. Since sine waves are periodic, this is a non-issue in this script, but in general this is important. Next, we have our training function, which is called full GD because it does full gradient descent instead of batch gradient descent. This is okay for this dataset because this dataset is quite small. Alright, so next we call our full GD function, and training is almost instant. Okay, so next we plot our loss as usual. So this looks decent. Next, we're going to do a forecast using the incorrect method. The reason I want to do this is because I want to show you what not to do. We're also going to do this calculation manually because the general form of the code is going to be helpful when we want to make actual forecasts. As an exercise, you might want to think about how to make this code do the same thing, but more efficiently. So first we assign the validation target variable, which is just the second half of y. We'll create an empty list for the validation predictions, and then populate this as we loop through the data. Next, we're going to set the index variable I, which indexes xtest, to 0. Next, we're going to enter a loop that continues while the length of the validation predictions list is less than the length of the validation target list. Once they are the same length, we know that we're done because we've made all the predictions to correspond with the targets. Inside the loop, we get our model prediction P. Now, this might look weird to you. Why not just pass in xtest sub I to the model and then assign that to P? Well, there are two problems there. First, xtest sub I does not have the right shape. Remember that the input to the model must be a two-dimensional array. But xtest itself is a two-dimensional array. So if we index xtest, we only get a 1D array of size t. Therefore, we need to reshape the array to 1 by t. That means one sample with t features. We can accomplish that by calling the view function and passing in 1 minus 1. Then we get the output of the model prediction, and that's also not the right shape. Because remember that, in general, the model returns an n by k output if we have n samples and k output nodes. In this particular example, we happen to have one sample and one output node, so this returns a 1 by 1 two-dimensional array. Therefore, to get the scalar value contained within it, we have to index the array at 0, 0. Finally, since the output value lives in PyTorch land, we want to bring it back to Python land by calling the item function. Next, we increment I, and we append the prediction P to our validation predictions. Next, we're going to plot our predictions against the targets. So this looks very good, pretty much exactly correct. But remember, this is still the wrong way of forecasting. Next, we're going to do forecasting the correct way. So if you just glance at this code cell, it looks almost exactly the same as what we had before. We start by grabbing our validation targets as the second half of y, and we initialize validation predictions as an empty list. The next line is different. Before, we just had an index I, and we used I to index xtest, the input data. But the problem was, we shouldn't have been using the true input data to predict future values of the time series. Instead, we'll set the variable lastx to be the first input vector. From here on out, we will no longer take any new values from the actual dataset. So next we enter the loop. Inside the loop, we do the same prediction as before. Remember that we have to reshape the input to 1 by t. Now this is where things change. First, after getting the model output, which we'll call P, I'm not going to immediately grab the value and bring it back to Python land. Instead, I'll do that on the next line, where I append the prediction to the list of predictions. So I index P at 0, 0, and then I call .item. So why did I do that? Well, I still need the P value to be in PyTorch land. In order to make our new input on the next iteration of the loop, we essentially have to shift all the values of the array to the left and then add the new prediction at the end. Of course, this entire array must be in PyTorch land and not NumPy land. So that's why I kept the P variable as it was returned by the model. Lastly, we use the PyTorch cat function, which stands for concatenate. I take everything in the previous input x, throw away the first value, and then concatenate it with P, the newest prediction. So that's how we update the variable lastx with our latest forecasted prediction. So let's run this. And finally, let's plot the predictions against the targets. So this is very interesting. So it appears, even though we are now making the forecast using the correct method, we still get a perfect prediction. Now remember that this time series has no noise. So you might be wondering, what happens if it does have noise? Let's go back and add noise and then run everything again. So let's scroll back up. Let's uncomment that line. And then let's go to runtime and run after. Okay, so here's the noisy sine wave. Here's all the other code. So you'll see that the loss is a little higher now. Loss per iteration still looks good. So here's where things get tricky. We're going to plot our incorrectly made forecast. As you can see, it appears to look pretty good. Our forecast even appears to smooth out all the noise. But remember, this is the wrong way to forecast, so it should be no surprise that these results are misleading. So let's go down to the correct way of making forecasts. Okay, so now we see what happens when we do a correct forecast, which is what happens in the realistic scenario. As you can see, the results are no longer as good because of all that noise. Interestingly, the model does learn that the pattern is periodic and that the true underlying function is smooth. So at least that's pretty encouraging.